Alrighty, so I want to start looking at what's known as the solubility rules. So knowing how to predict whether two ions will form a solid compound or remain as ions is really important. It's going to allow us to predict the products of our precipitation reactions. The precipitation reactions are also known as double displacement reactions, but we'll get there in just a minute with that information. So for now, the goal is to start using and becoming super comfortable with the solubility rules. This semester is a little different, right? We're online and I am not watching you take the quiz. However, when we have the in-person class, traditionally we have the students memorize the solubility rules. So this is just a heads up for you. The solubility rules are listed there. As you go into your next courses, that'll be the expectation for you. But for now, you consider yourself lucky. You can have the solubility rules out when you take that quiz. You just have to know how to use them. So how this works is you'll be given a compound or you'll predict what the compound looks like. And then you have to break the compound into its ions. So here, well, copper is a transition metal, so I just don't know. But then sulfur is in group 6, so I know that it's going to be S2 minus. And then since it combined in a 1-to-1 ratio with sulfur, that tells me I'm dealing with copper 2. Now, you're going to look through each rule. If you don't like my rules, there's other versions of solubility rules. Your lab manual has a different version. You can Google it. There's all kinds of YouTube videos about how to memorize them. So I know from experience that copper sulfide is an insoluble compound. And when something's insoluble, it forms a precipitate, and it's considered a solid. So when I write my reactions, we're going to get there shortly, this would be followed by an S. So the S stands for solid, but it also stands for insoluble or precipitate. And I said I know from experience. Well, you're like, I don't have that experience. How do I know? So if you're using this set of solubility rules that's in the lecture handout, you want to find a rule that applies to either the cation or the anion. So I'm looking at Rule 7, and Rule 7 specifically tells me that all sulfides are insoluble with a couple of exceptions. Copper is not one of the exceptions. So eventually you'll know, especially with some of the more common ones, you'll start to kind of memorize them. You don't have to memorize the numbers of the rules. You have to just memorize what's going to happen. So in a similar manner, first step on these solubility problems is to separate the given compound into ions. So here, because calcium's in group 2, I expect a calcium 2+. Hydroxide is one of the polyatomic ions that you already memorized. And so we have an OH minus. And we can check those charges. We can redo our crisscross and verify those charges. Go through the rules again. And so you're going to come across a rule about hydroxides. On this list, it's Rule 6. In general, hydroxides tend to form solids. However, there's several exceptions. Group 1s, so anything with sodium hydroxide, potassium hydroxide, lithium hydroxide, those would be aqueous. And there's a couple of exceptions from group 2. So calcium is one of the exceptions. Calcium hydroxide is considered to be a soluble compound. So when something's soluble, it means that if you have a beaker of it, it's not on the bottom. It's not something that's opaque. It's not something that's floating around. You're not really going to see it. What's in the beaker is a whole bunch of calcium ions floating around and a whole bunch of hydroxide ions floating around. They're not together. They're they're completely separate. They're doing their own thing in there. And that's what it means to be soluble. And so let me just jot that down. They're present as ions in water. And because of that whole water piece, you need the water to form the ions if they're going to form. Think like agua or aqua. And we call this aqueous. Soluble compounds that break into ions are known as aqueous. And that's where we're going to get this AQ from. So if something's soluble and you're writing your reaction, you need to follow it up with AQ. Let's do a couple more. So this one, I'm like, yes, one of my favorite ones. When I took CHEM100, I had the worst time trying to memorize my solubility rules. There are a couple rules that really stuck out at me because there was no exception. So for instance, rule 1, rule 2. Rule 1 tells us that if it has a group 1 cation in it, like sodium, potassium, lithium, always soluble, no exceptions. So I would always look for those on my test. In a similar manner, I think it's rule 2 on your list. Rule 3. Anything with a nitrate in it is always soluble. So nitrates are always soluble. No exceptions. I guess I kind of like the rules that don't have those annoying exceptions. When you look at the compounds that they give you in lab, or if you ever go back and have a chance to look at the stock room or you visit a lab, you'll see that a lot of the solutions that are already prepared have nitrates in them. And that's because we know that the stuff will dissolve if it has a nitrate ion in it. So it's like kind of like, oh, what am I going to mix up? Let me pick something with a nitrate because I know I won't have any issues. So at the end of the day, nitrates are always soluble. So we're going to put AQ after this compound. I didn't even break it down. It would be zinc 2+ and NO3-, but since I saw the nitrate in there, I was like, oh good, it's soluble. All right, let's do the next one. So again, let's break it down. We have calcium, which is Ca2+, and we have phosphate. I knew the +2 because calcium's in group 2 of the periodic table, the vertical column. If I forgot what was going on with phosphate, I could try like undoing my crisscross because that 3 came from the phosphate anion. All right, so we need to look for a rule involving calcium or phosphate. And if we go through, or you'll memorize your version or whatnot eventually, this is going to be insoluble because on yours it's rule 8. And it's carbonates and chromates, phosphates are insoluble except if they have a group 1 because group 1s always cooperate. So we'll call this insoluble. And therefore, it should be followed up by an S. So what I'll have you all do, I'm going to stop the video here and film the next segment, but I want you to take a quick break, or a break from watching the video, and do the rest of the problems on page 1 before you start the video up again. So start working with the rules, make sure you're understanding what's going on, and then I'll go through the next step maybe a little bit faster, and that way you can check your work and we can start building on this idea. Alrighty, so hopefully you attempted all of these problems and you have some preliminary answers written down. As I was mentioning before, as a student, I found memorizing these rules to be really difficult. I don't have the best memory, but a couple of them really, really stuck with me. And so anybody that has a group 1 ion is always soluble. Any compound that contains a nitrate is always soluble. And any compound that contains ammonium is also always soluble. So for me, I was like always zoning in on those. There's no exceptions to these. Those were my guaranteed points, because the rest of the rules would just like turn into gibberish in my head. So let's start there. So what I would do is I'd scan through these and I'm like, ooh, I see a group 1 cation, because this would break into K plus, and I know it's +1 because it's in group 1. And this would break into sulfide, so S2 minus. So I'm like, yes, group 1 cation. I know it's soluble, and I know I can write it as being aqueous. No, nitrate. Yes, nitrates, there's no exceptions. They're always soluble. So that means that they don't hook up in solution. The mercury stays over here and the nitrate stays over here. The ions remain separate. And then we have one more that's kind of like a easier one with the ammonium perchlorate. And so just because of the NH4 plus part, we know that it's soluble. So tackle the ones that you find easier first, and then let's go back and start looking at some of the other ones. And again, you have those solubility rules right there, so you'll want to reference them. If you're not seeing what's going on, separate it into ions. So I know that this is hydroxide. And then this 2 must have came from up here. So this is going to be manganese 2 plus hydroxides. Hydroxides tend to be insoluble. There are exceptions, because those don't have exceptions. So for instance, sodium hydroxide would be soluble, but in general, hydroxides are insoluble, and so this would form a solid in solution. So I'll put an S there. Although it's not one of my favorite rules, one of the higher listed rules, I should give you some numbers here. Again, the numbers are just there to keep stuff organized. So per rule 3, we know that anything containing chlorate is always soluble, no exception. And so I'm going to follow that up with AQ. Just going to write down rule 6 over here for the hydroxide rule. So this is going to be aqueous, which is going to be AQ. Aqueous, or I'm sorry, instead of call it soluble or insoluble. So aqueous means soluble. All right. Over here we have calcium carbonate. I just want to find the rule. Carbonates tend to be insoluble, and that's going to be rule 8 on your list. So again, over here I'm thinking about carbonates, and for the most part, they're insoluble. There are some exceptions, especially our group 1. So with sodium carbonate, it'd be soluble. But since it's calcium carbonate, it's insoluble. So I would do this with an S for solid. Insoluble means it forms a solid or forms a precipitate. So we're getting there, just a couple more. So we have zinc sulfates. Zinc sulfate. Sulfates tend to be soluble. That's going to be rule 5. So this would split into Zn2 plus and SO4 2 minus. This tends to be soluble with exceptions. Zinc is not one of the exceptions. And I should do that on the other ones too, just in case, so your notes are complete. Insoluble with exceptions. And the other one, this one, insoluble with exceptions. All right, so just one more to go. Hopefully everybody's hanging in there. And if you're not when we get to the next part, you'll have a chance to practice this even more because we're just going to keep on building on this. Or, you might want to stop the video, maybe do some of the Alex practice specifically on this topic before you start the next part of this. Last one, we're going to do mercury sulfate. So mercury is super tricky, but sulfate I know is SO4 2-. And so since this is a 1-to-1 ratio, then to assume that my mercury had a 2+. So this is mercury 2 sulfate. Sulfates tend to be soluble with exceptions. If you comb through, and again, the numbering is not critical, just for reference. If you comb through Rule 5, they list exceptions. Mercury, it says, is when a sulfate is with mercury, it's moderately soluble. So at that point, it depends on conditions. How much did you put in there? How concentrated was your solution? What temperature are you at? So there's a lot going on. How much did you mix it? So for this one, I'm going to call it a solid because moderately soluble isn't that good. It's not like it's going to dissolve really quickly, like sodium chloride, table salt, dissolves really easily. If I hear moderately soluble, I think I'm going to have a tough time getting this to dissolve. So my rule of thumb, students always ask me about it. If it's moderately soluble and you're doing a problem, mark it as a solid. Because most likely you're going to see something, maybe you have to hold it up to the light and really look for it, but you're going to see some kind of precipitate in that reaction mixture. All right. All right, so now we're going to build on the solubility rules and use it in our discussion of precipitation reactions. Precipitation reactions fall under the category of double displacement reactions. How do you know it's a double displacement reaction? Well, one clue is that you have two couples. And what I mean by that is you have lithium and iodide and they're together currently. So I consider that to be a couple because there's two pieces to it. And they don't necessarily have to be single, just binary compounds. This is a couple too because we have sodium and carbonate. So when you're trying to identify, is this a double displacement reaction? You're gonna look for two couples. So on the lecture handout, there's a picture of two people like dancing. You'll hear me call precipitation reactions, or you'll hear me say do-si-do. And this is because when I took this class, I lived near downtown San Diego, and there was a church. Like the window to my room in my apartment, I could see and hear the activity hall of a church. Like I live right next to a church. And on Tuesday nights, it was so cute. They'd have all these older people that would go there and do square dancing. And precipitation reactions, specifically the double displacement reactions or the ones that we're doing here, reminded me of the square dancing that took place in the church. So let me explain a little bit more. And then they'd always, in square dancing, they do like the call out. So they'd say like, do-si-do-si, do-si-do, like switch your partner, whatnot. So what I mean by that is like, you have two people, right? They came in together and then they start dancing. So at some point during the dance, they're gonna separate. So we're gonna have them separate into lithium. The charges are really important. So lithium +1. I'll write that down just in case. and then iodide -1. So we know the charges because of the columns, the groups in the periodic table. Same thing over here. We're looking at barium, like, okay, that's a 2+. And sulfides in group 6, that's going to be a 2-. So, and if it's a transition metal, you're going to want to double check, make sure you're getting the charges correct. We know that they're willing to split up because they're aqueous. That's the definition. If something's soluble or aqueous, it's broken into ions. So we have this beaker, which is like the activity hall, and they come in as couples and then they start splitting up. And then they're going to do-si-do, they're going to switch partners. So positive and negatives always hook up. So lithium is potentially going to hook up with sulfide, and barium is going to hook up with iodide. So now we need to reform couples on the other side. So we have Li+1, and so off to the side somewhere, it's not part of your final answer, but you have some scrap work to do. You're like, okay, well, I have Li+1, and I need to crisscross it with S2-. So remember the whole crisscross thing. I told you to come back. So I crisscross that, and I get Li2S1, but I'm not going to write the 1 in my answer. So in my official answer, I'm going to have Li2S. Leave room. I should have left a little bit more room here. Leave room here because we're going to balance. And leave room here because you're going to have to tell me if it's aqueous or solid. All right, in the middle, the other two people that do-si-doed, right, switched partners. The barium and the iodide, we need to reorder this because remember when you do crisscross, the positive one always has to go first. So we have barium 2+ and I-. So just make sure the positive is first. And again, I'm just doing this off to the side because this is scrap work. This is not part of your final answer. Crisscross those, and we're going to get BaI2. So far, so good? Should answer your question. Alrighty, now at this point, you're going to go back to your solubility rules and you're going to check. Is this going to be solid or is this going to be aqueous? So for instance, here with the lithium, that's one of my favorite ones, right? Group 1s are always soluble, so I know that this is aqueous. And then with barium iodide, most iodide-containing compounds are soluble. Just trying to get the number on that rule for you. So you're going to go down to, what number? Rule 4 tells us that this is soluble. So I'm going to put AQ. It's not one of the exceptions. What does this mean? This means that nobody formed a solid. So if you're in the lab and you mix these things up, it looks like nothing happened. It's actually like really, really boring. You mix like a solution that looks like water and you mix another solution that looks like water and nothing. You're like, what did I do wrong? You didn't do anything wrong. It's just that they didn't want to form a solid. So when you have, let me do it in a different color. When you have two aqueous products, you figure that out, you're done with your problem. All you have to do is write no reaction. So if it's two aqueous products. And the good news is if it's no reaction, you don't have to balance it. So typically on tests, I know it's a little bit different now, but typically on tests, all I'm looking for is no reaction. I didn't really care how you got to that point because on these, if you recognize that there's no reaction, that's good enough. Let's check a couple more out and see what's happening in some other examples. They come in together, but they're dancing, right? So they're gonna split up so they get do-si-do. So we got K plus, Cl minus, Ca2 plus, and S2 minus. The positives always hook up with the negatives. So they're gonna switch partners. You're gonna redo your crisscrosses. So on one of them, and again, this is all scrap work, I have K plus and S2 minus. So I'm going to crisscross those, and I get K2S. On the other one, reorder it, so your positive cation, your positive ions first, calcium 2 plus and Cl minus, crisscross it, and I get CaCl2. So I'm going to write those in here. Give yourself some extra space. So K2S and CaCl2. Group 1, yes, right? Aqueous. That rule 4 again, it includes chlorides. Typically, if it has a group 7, it's usually soluble with a handful of exceptions. But by rule 4, we can identify that as being an aqueous compound as well. So at the end of the day, we're done with this problem. All we need to write here, acceptable answer is no reaction. Letter B. Let's see if the next one actually happens, right? Split them into ions. So we got chromium, transition metal. So I don't necessarily know what's going on. Bromide's group 7 though, and I feel confident about that. That's a -1. So the 2 that we see down here, kind of undoing the crisscross, that 2 must have came from up there. Sodium, I know, is +1. And then this is why it's important to have those polyatomic ions memorized. And we have carbonate. So chromium, the positive chromium potentially hooks up with the negative carbonate, and the sodium and the bromide combine. So I'm not even going to go over to my scrap side right now because this is a +2 and this is a -2. So if I crisscross them down, I get 2 and 2, which reduces down to 1 and 1. So whenever we have the same charges, we know they're going to combine in a 1-to-1 ratio. So I'm going to predict chromium carbonate, but by all means, take your time and figure that out. Reorder this. Sodium has to be first in this middle combination here. And why I'm standing here, sodium's a group 1. So I'm going to identify that as aqueous. So carbonates tend to be insoluble. That's one of the lower rules. Rule 8 for y'all. So since carbonates tend to be insoluble with a couple of exceptions, but this is not one of the exceptions, this is going to be a solid. And so what does that mean? Really boring stuff in A and B. You mix this up in the lab, you're going to be disappointed. But when you get to C, this is where it gets like really exciting. It kind of looks like magic. You typically have 2 transparent solutions, like no floaties in them. And then all of a sudden you mix them up and all of a sudden you see all of this solid just form. And the solid will be your chromium carbonate. What I like to think of it as, I know this is really corny, you guys know I'm weird, is that these guys now fell in love. They like found somebody at that dance and they're like, oh, I'm gonna stay with you forever. Because when we think about what's going on with the solid, the ions are stuck together now. They're not wanting to break apart even if you put water there. So it's like one of those couples that's madly in love and won't separate from one another. These guys, not so much. So in the solution that's in the beaker, we're still going to have sodium ions and bromide ions floating around separately. When they're aqueous, they're not in love and they're just willing to separate in water into ions. Okay, if you have a solid, you need to balance it. We're almost done here. Solid, you need to balance. So what I'm noticing with balancing is I have 2 sodiums right here. So I'm going to put a 2 out front here. That's going to give me 2 sodiums, but the 2 also has to be distributed to the bromine. So that gives me 2 bromines. But if I come over here, I already have 2 bromines over here, so that's good. 1 chromium, 1 chromium. I don't like to separate my polyatomics. There's no point. So I got 1 carbonate over there and 1 carbonate over there. So everything's balanced just by the addition of the 2. So this would be, there's not even enough room for me to box it, but this would be the final answer here. Let me underline it. So all of this written out right here is your final answer. This is work, scrap work, and anything that you did like for crisscrossing purposes is scrap work. Your final answer is underlined. Alrighty, so if you haven't done so already, what I recommend is that you stop the video and you do D, E, and F on your own. Try to attempt them and then watch. Once you get the answers down, come back and watch how we set them up and check your work. I'm going to go through them a little bit faster because I do want everybody to do them ahead of time. So on letter D, we're going to have sodium and hydroxide, Na plus and OH minus. I don't know the iron, but chloride's -1, which means this 3 must have come from the iron. So it's iron plus 3. We're going to do-si-do them. Sodium hooks up with chloride and iron hooks up with hydroxide. For the sodium chloride, it's +1 and -1. So I'm going to have NaCl aqueous. For the iron hydroxide, be careful on this one. You have Fe3 plus and OH minus. You have to crisscross those 2 things. Since hydroxide is a polyatomic ion, you do need parentheses. So this 3 goes to the outside of the parentheses. So my other species here will be iron 3 hydroxide. And if you look through your solubility rules, that's expected to be a solid. So we definitely have a reaction here. We definitely see something going on. We need to balance it. There's 3 chlorines here. So I can't put a 3 here, that's not allowed, but I can put a 3 out front. So that means I have 3 sodiums and 3 chlorides when I distribute. I need to fix the sodium, so I'll put the 3 out front here. That gives me 3 sodium and 3 hydroxide. But if I come over here, I have 3 hydroxide, so we're good. And then 1 iron on both sides. All right, so that one's done. Next one, Na plus, and you have nitrate, NO3 minus, K plus, and Cl minus. So when these do-si-do, we're going to have sodium chloride again, just like in the previous one. And we're going to have potassium hooking up with nitrate. So we have NaCl, which is aqueous because it has a group 1, and potassium nitrate, which is also aqueous because my favorite rule, group 1s are always soluble. At the end of the day, the answer to this one is no reaction. This is one of those boring ones. Don't have to balance it if it's no reaction. Let's do this last one here. So we have ammonium, NH4 plus, this 2 came from the sulfate. Sulfate has a charge of 2 minus. One thing I do recommend, especially if the nomenclature part is still, something that you feel like you need to work on, is when you separate these things into ions, redo your crisscross just as a check. So I'm like, okay, the 2 would come down here. Like, make sure you got the charges correct. So you have Cl minus, and the strontium is going to be a 2 plus. Do-si-do. So ammonium is going to hook up with chloride, and strontium is going to hook up with sulfate. So this is a +1 and this is a -1, which means they combine in a 1-to-1 ratio. The positive always has to go first. So I'm going to have SR2 plus and SO4 2 minus. Parentheses, because it's a polyatomic, we have a 2 and a 2. So SR2, SO4 2. But the 2's can be reduced down and I can get rid of the parentheses. So this is going to be SRSO4 at the end of the day, because I reduced the 2's, and with 1's you can get rid of parentheses. Ammonium, always soluble. Strontium sulfate, so it's going to be the sulfate. You're going to want to look on your solubility rules. That's going to form a solid when it combines with strontium. That's one of the exceptions. All right, so since we have a solid, we have to balance. Let me take you through my thought process here a little bit. I want to keep ammonium. I'm going to put a blue cloud around ammonium. So over here I have one of these guys. And over here I have 2 ammoniums. So that's my first problem. So let me fix that. I'll put a 2 here. So that way now I have 2 ammoniums. That also gives me 2 chlorides, but I'm okay with that because there's a 2 there. And then sulfates, let's see how many sulfates we have. So this is just 1 sulfate. And then over here, we only have 1 sulfate. So that's good. And strontium, if we look at strontium, there's 1 strontium on both sides as well. So it's balanced just with the addition of this 1, 2, this 1 coefficient out front.